So we have a bunch of panelists today to talk about FDP. Let me introduce them, and then they will get started here. So we have John Michael Hands. We have Imram. We have Rory, Jonathan, David, Jaja, and Steve Wells. And so with that, I'm looking forward to a great session. And John Michael, you want to kick it off here?
How much time do we have each?
Like 6 minutes, roughly.
Go. Well, this is good. Well, this is good because I think I did it in 5 minutes in the OCP storage work group. Yeah, so I mean, Mike Allison and I think when we were at Intel, I think we were some of the first people to hear about FDP when Ross had this idea. So I came back, I'm at FADU right now doing product planning. And I really did some of these experiments just to kind of figure out how FTP worked. Most of this stuff was just personal curiosity and kind of led me to some experiments. And Ross thought they were pretty cool and wanted me to talk about them. Obviously, some of the use cases for FTP are these cloud-native environments where you have containerized workloads, virtualization, and you have the ability to kind of tag data and use it in different spots. And one of the things we're going to talk about is multiple namespaces. The specific experiment I did was using FTP in multi-namespaces. So one of the benefits, obviously, is this reduced noisy neighbor effect. If you have multiple namespaces in FTP, and you have each namespace, which we're going to describe, has an RUH per namespace, then it kind of reduces this noisy neighbor effect by putting all the data from a VM in the namespace with it in the same RUH. When you do this, the optimized garbage collection, you can reduce WAF, which is the whole point of FTP, is to reduce WAF, improve performance, improve endurance, and improve quality service. Namespaces is very good for application developers because it's a very easy way to manage. You just, especially in this virtualized environment where you can just have one namespace per VM, it's very easy one-to-one mapping. And the performance sharing is one where you can, in FTP, if you have one VM that has a RUH per namespace, if the other VMs are not active, you get performance benefits and bursty performance in that one VM. So it's much better than like before with like sets or something where you're like very rigid, a certain number of die per channel, and you're not going to get all the performance benefits. So this was just experiment. First we did in FIO, which was basically take a bunch of different sequential write workloads of different block sizes and throw them to the drive. And with FTP off, you have high WAF. This like 2.5 WAF. With FTP on, you get full bandwidth, like 5 gigabytes a second. So this just shows like in a workload where you have a bunch of different sequential write streams and they're all different sizes and velocity, that FTP helps a tremendous amount by reducing the WAF to 1. So I thought, okay, can we do this? Doing this in FIO is kind of clunky right now because you have to use some of the plugins for the NVMe command. So I thought, okay, well, can we do this in a virtualized environment? And so with FTP enabled, I want to have 8 namespaces, 8 RUHs, 1 namespace per RUH. The whole idea is no software development required because we don't want application developers to have to go through any work. They can just create a namespace with one command line and NVMe CLI and not have to worry about anything else. And so this is one of the whole points because application development is, there's stuff like CacheLib and things that are support for FTP that are enabled already, but it'd be very nice for application developers to not have to do any work and get all the benefits of the WAF. So I made a Proxmox virtual environment, and I have 8 VMs, and you can see this drive. I have a 7.68 terabyte WD-SN861 with a FTP enabled, and I've created 8 different namespaces on there. So the first thing we had to do is the control, and I'll kind of walk you through that. But to calculate WAF, reminder, we have to basically grab physical media units written from the OCP C0 log page, and then we use data units written for smart, and we can record before and after. I have a little Python script over here. You can't see it, but you'll be able to download it. That basically just pipes the WAF data to a CSV while you're running this workload. It's very nice with FTP enabled. You can run one command, NVMe FTP stats, and get the WAF right away. So this is very, very convenient. So with the control, I basically have a single namespace, single drive, 7.68 terabytes with FTP off. And I'm going to format it with LVM and then give each of these 8 VMs with virtio a /dev/vdb is what they show up on the VMs. I had to be 940 gigabytes just because of the size of the RUH. You can't get exactly, obviously 7.68 divided by 8 is 960 gigabytes, but you can't do exactly that because of the RUH size. And then, so we run this playbook, which is going to collect the smart, kick off FIO and all these VMs, which is a little bit harder, to do in this. I have an Ansible playbook that will go do this, and I have a link in the description. Ensure it started correctly, which is one of these challenges with FIO and all these VMs, to make sure it's actually running, and then make sure it completed, and then collect the data. So I just picked a kind of random workload, some 4K random reads, and then kind of tried to simulate that other workload with a bunch of different sequential write block sizes at the same time. And you can see here, the WAF was 1.7 with 2.2 gigabytes a second of write bandwidth. And so next, we have to turn on FTP. So the way that we do this, and I have a blog on the FADU blog that shows how to enable FTP. So the first thing you have to do is delete the namespaces. And that's this little script for, we're going to make sure we delete all the namespaces on the drive. The second is enable FTP. This is this nvme set features command. And you have to do it in this order. If you try to enable FTP while there are namespaces on the drive, it will not work. And then you can do this nvme FTP config. That will actually tell you what the drive supports. And this drive supports 8 RUH initially isolated. And so you can say, okay, this drive supports 8, let's make 8 namespaces. And so this next script is basically just going to create 8 namespaces, and this -p here will tag an RUH to the namespace. So it's very, very nice and clean. Just one line in NVMe CLI to basically attach an RUH to that namespace. And you can see here with NVMe list, I can see now I have one drive, 8 namespaces. So we're going to run that same script again. And you can see here, some of these VMs are hitting 1.7 gigabytes a second of bandwidth in just the VM, in a single VM, which is amazing. So it works. We reduced the WAF to 1, which was kind of nice when you design one of these experiments and you do it and it works the first time. You're like, yes, okay, I can go on to the next one. This background random read increased by 182%, the write bandwidth increased by 150%, the endurance by 170%. Again, this is the benefits of WAF. When you reduce WAF from 1.7 to 1, you get all the benefits of performance, you get all the benefits of endurance, you get all the benefits of quality service. As you can see, this was all the way up to 5.5 gigabytes a second on this bandwidth, with 8 VMs running all these FIOs in each VM. So, and again, this was fun. In the future, obviously, with SRIOV, it would be a little bit cleaner. I could just give the namespace to the VM directly instead of having to use virt.io. There's some nuances of trim and some stuff that doesn't probably work properly that I need to file some bugs upstream. But this was, again, this was a fun experiment, mostly for me to learn FTP. And yeah. So next.
Thank you, John. So what I'm going to talk about is basically what power improvements we can achieve by using FTP. So today we already have Gen 4 devices. We also have Gen 5 devices. And in the future, we're going to have Gen 6 devices. So the bandwidth from Gen 4 to Gen 5 will double. And from Gen 5 to Gen 6, it will double, right? But the actual performance that you can achieve on a product really depends upon the form factor you're using, right? So even though the interface might be able to actually achieve really high performance, what you can achieve on the product, it really depends upon the form factor power limit. So you might actually start the product with maximum performance, but very soon the thermal throttling will kick in and the performance would be much lower. So, and to improve the sustained power for longer, what you can do is actually implement FDP. FDP will basically increase the garbage collection in the backend. It will reduce the WAF. And in turn, you will actually have that higher bandwidth for longer, right? And this particular feature will be very important for TLC drive, but I think it will be even more important for QLC drive because the power on the QLC drive will be higher. And to achieve better performance on a QLC drive, FDP would be a must-have. So here, basically, I'm showing some measure data. So we implemented FDP on our products. So on the graph on the left basically shows a write amplification graph with and without FDP. So the blue line that you see over here is basically the write amplification with FDP. And you can see it is very close to 1. And when the FDP is not turned on, it is around 1.8, right? So what is happening in the background is basically it is writing sequentially, and there is no garbage collection, right? That is how you're getting better WOF. So you're getting almost WOF of close to 1 with FDP. The graph on the right basically shows the sustained bandwidth that you can have with and without FDP. So with FDP, you can actually have a sustained bandwidth of 3 gigabyte per second on a QLC drive. And for a case where FDP is not enabled, you will get about 2 gigabyte per second, right? So you can have 30% improvement when you implement FDP on your drive. So when you actually take this number, and the next slide I have over here, basically the top table shows the data that I just mentioned earlier in terms of write amplification and bandwidth that you can achieve with and without FDP. But the interesting part is the power. So if you look at the table at the bottom, and to achieve roughly 3 gigabyte per second with FDP, on the max side, it takes about 15.5 watts, right? And without FDP, you can achieve 2 gigabyte per second, but it takes 22.8 watts, right? So on the max power, there is a 30% difference. So you're getting a higher bandwidth, which is 30% higher bandwidth with FDP, and you get 30% lower power with FDP. So the overall impact of FDP is double, higher bandwidth and lower power. And you see the same trend on the average power, right? Where the average power is 19% lower with FDP as compared to without FDP. So when you actually implement FDP on your system, you basically delay the thermal throttling, and in turn what you're doing is you're getting a longer time of sustained high performance. That is one benefit you can get because the thermal throttling will be delayed. The other thing that is the benefit is you can actually run your fan slower, right? That is another benefit you can have of FDP, right? So moving on to overall in terms of call of action, I think once you go to Gen 5 and Gen 6, I think having FDP on your product will be very important because it gives you overall better solution with higher sustained bandwidth and lower power. And again, all the solutions when you're looking in the future, if you're looking for a product on the enterprise side, I think FDP should be there, and you should be looking for a product that supports FDP. So we, Fazan, just released an Gen 5 product that will support FDP. Okay, thank you.
Morning. All right, so I wanted to talk today about what storage architects should know about flexible data placement, all right? You've heard a lot of people mentioning WAF, and I'm just gonna do a little first principles here. Flash media does not allow overwrite in place, and so when we write new data, we have to write it to a new location and invalidate any old copies of that data. And that leads to this fragmentation of superblocks denoted by the different colors of both valid and invalid data in the top illustration there. And we have an internal process, garbage collection, that moves, copies those remaining bits of valid data from the fragmented blocks, puts them into a new block, and that allows us to erase, free up those previously fragmented blocks for reuse. And this induces wear, it steals bandwidth, it's generally a bad thing. So you want to reduce WAF as much as possible, and that's one of the primary motivations for the development of flexible data placement. Okay, so what's the promise of flexible data placement? It's a mechanism that allows you to try to organize your data by its expected expiration time, right? So in this example, the top illustration, once again, we've organized data that's going to be either overwritten or trimmed, deleted into different blocks and denoted by the different colors. And in this particular example, if you were to, say, trim or invalidate the green block of data, in an ideal case, you'd be able to reclaim a block of flash media without any movement of data at all, right? So, great. Flexible data placement is a highly configurable specification, and it allows you to organize data either down to the die level or at higher levels, such as the superblock level. Different drive vendors are going to have different implementations, different options supported within their devices. And so one of the key messages I'm trying to impart is if you're trying to embark on flexible data placement, talk to your vendors, see what they support so that you don't make decisions that aren't supported by your devices of choice, right? I'm going to focus the rest of this presentation on superblock level flexible data placement. And there's a couple of reasons for that. Number one, it's what I hear the most inquiries about. And number two, to enhance the reliability of our devices, almost all device manufacturers perform cross-die RAID. If you're doing down at die level placement, it's very difficult for us to do that. Also, striping across multiple die in a superblock allows us to give higher levels of performance without additional host overhead or management of the performance. And finally, there's some write buffer and power loss protection implications if you're doing the die level control. So once again, for the rest of this discussion, I'll be just talking about the superblock level format of flexible data placement. And not on the slide, but I should point out a real advantage of this is that if you do nothing but enable flexible data placement in the superblock mode, it acts just like conventional SSD. So there's no downside whatsoever, only potential upside here. And as has been mentioned, some upsides you can actually leverage without doing any work to your code at all. Okay, so what are some of the things I think you guys should know about flexible data placement? First and foremost, there are few hard guarantees, right? And ultimately, what it's saying is when you supply a write with a placement ID, we guarantee that that write will not be mixed with other writes with different placement IDs on initial placement. Beyond that, it's all sort of options up to the individual device, whether it supports persistent isolation or only initial isolation, and many, many other different aspects. I hear customers trying to align data structures to the actual reclaim units themselves, but this is kind of not a best practice in my opinion. Flash varies from generation to generation, from vendor to vendor. You really shouldn't be making any assumptions about the size of the superblocks or the blocks. They're rarely a power of two, and in general, they're growing, right? You also shouldn't try to rely on data ending up in the current reclaim unit, even if you're polling to see how much space is left in that reclaim unit, and even if you're using queue depth of 1. Why do I say this? It seems like that would be something you could do. Well, the most common way to implement flexible data placement today is using IOU ring. And IOU ring has a very nice optimization that tries to amortize the transition cost from user space down into kernel space by holding on to IOs in a lockless, singly linked list. And because it's a lockless, singly linked list, when it actually does submit down into the device, it is a LIFO, not a FIFO. Now, this is how it works today, and of course, Linux is very dynamic, may change in the future, but unless you control the full I/O path, you shouldn't make assumptions on the order things are going to happen. All right? Superblock size can be quite large. In case people don't know, the trends today are in the gigabytes for superblock sizes, and the number of reclaim unit handles supported by a device is fairly small. It's likely to stay small just because of the resource implications within the device to support, say, hundreds or thousands of reclaim unit handles. All right, next 2 points. No guarantees between interlock on trim and garbage collection. There are some race conditions that exist there. And there are also other race conditions that can happen if you're running deeper queue depths for higher I/O, which I'm not going to go into. So with all this in mind, what are the things that really map well to flexible data placement? Well, first of all, if you want to try and minimize the effect of those race conditions, Over provisioning helps. It's a cost, of course, but this decreases the likelihood of races that could affect and induce unnecessary write amplification. If you're doing direct LBA access, once again, the best thing you can do is group data by expected expiration time, if possible, log structured writes, and circular buffers generally map very well, give very good results with flexible data placement. An example of that, RocksDB. In fact, we just implemented and submitted to open source a plugin for RocksDB. There was a press announcement on at this show where we're getting fabulous results. We have a live demo of it out on the show floor. Go by the Kioxia booth and take a look if you're interested in RocksDB working with FDP. Transaction journals, copy on write file systems, snapshotting file systems all work really well with FDP. If you can separate hot and cold data, good advantages there too. Typically, data classification is really tough to do a priori, but once again, copy on write storage systems that perform application level garbage collection, they have very good hints as to what's cold data. It's the stuff that didn't change and had to be garbage collected out. All right, if you can't afford to directly change your applications, if you don't have times, whatever, this is one of the beauties. You've heard already about how you can do this. You can take advantage of FDP without changing your code at all. It's what I call the low-hanging fruit. It's defining a default placement ID for different namespaces and then pointing different applications to different namespaces. There was a VM example of this. Other examples of this, TempFS would be a good thing to put out on its own namespace. And so if you have things that you know are hot, separate them out from your cold data. You don't even have to change your code and get some pretty good benefits from it. Okay, I apologize for this slide. I apologize because it's simulation results. Like I say, we just announced support for device with FDP. We have devices running live demos now. I didn't have a real device to perform the test on in time to submit my slides. But in the upper left-hand side, you see a traditional drive running 8 circular buffers with 8 different expiration times, getting a WAF of over 2.0. The WAF that you'll see depends upon a lot of things, such as the over-provisioning of the drives, but WAFs in the 2.5 to 3.5 range are actually fairly typical in conventional drives. Top right-hand side, I separated out those same 8 circular buffers into 8 different placement IDs. Perfect near 1.0 WAF results there. Lower left-hand side, I had 2 of the circular buffers share a placement ID, but they still had similar expiration times or overwrite times of the data. And once again, you get near perfect results. So you don't have to separate out things perfectly, but it helps. Lower right-hand side, the final graph here, this is where I had 2 of the 8 circular buffers sharing a placement ID, but they had radically different expiration times. The point here is you don't have to get it perfect. Once again, this is a really good WAF result, getting down to around 1.2 versus over 2. So in short, organize your data as best you can. Don't make any real hard assumptions on where data is going to land, and you have the potential to drastically improve performance and endurance of your devices with flexible data placement. Thank you.
Hi, I'm Jonathan Hughes, an SSD architect with Solidigm. I'm going to talk about flexible data placement best practices. We're going to start with an exploration of reclaim unit size and with consideration for the default reclaim unit handle write performance. and then look at host software and SSD best practices to avoid the penalties of what I call unmanaged FTP. So for an SSD vendor, supporting a reclaim unit size of a superblock is ideal from a complexity perspective. However, some SSD consumers may realize additional value by using a smaller reclaim unit. However, with a smaller reclaim unit comes a reduction in write performance as there's a loss in parallelism. So the host would have to write multiple reclaim units in parallel in order to achieve full write performance. With an FTP SSD in a host, it may be attached to applications that are FTP optimized, and also to legacy applications that are FTP agnostic. And those FTP agnostic applications will be using the default reclaim unit handle. If that default reclaim unit handle is backed by a small reclaim unit, then those legacy applications will not be able to extract the full performance of the SSD. For the single reclaim group configuration, there's a lot of flexibility toward defining a reclaim unit size. Example 1 is a small configuration shown in blue, where you've got 1 block per die across all the channels. Example 2 is a super block configuration shown in orange, which is 1 block per die across all the die. And example 3 is a proposed configuration shown in green. That's 1 block per die across a subset of all the die. So the reclaim unit size is a trade-off between capacity and performance. And it may be, you may consider having a reclaim unit size for the default handle that's a full super block, but then smaller reclaim units for the remaining reclaim units. But this drives up complexity in both the SSD and the host software. Instead, we could consider a reclaim unit size that is smaller than a super block, but still provides full performance on a single reclaim unit handle basis, and thus driving down complexity, but still being able to realize the potential value of that smaller reclaim configuration. Okay, switching gears to best practices for avoiding the penalties of unmanaged FTP. FTP, as we've seen in prior discussions here, offers compelling value for driving down the write amplification factor, or WAF, and which in turn improves performance, quality of service, and endurance, and power. But to achieve these increases, we need to have the host manage reclaim unit handles by employing one of several techniques to separate the writes into either by logical range, or by velocity, or by data lifetime. And to enable FTP on an SSD without taking any of these strategies into consideration can actually drive higher WAF than even a traditional SSD. So let's explore how that could be true. So for a typical SSD, you've got some small amount of capacity devoted to internal system data, the vast majority of the capacity allocated for user data, and then again, some additional capacity for over-provisioning, or OP. The OP is used by the SSD to accept new writes when the logical capacity is full, and to perform garbage collection. And in this example, we have 2 reclaim unit handles that are randomly writing the full logical space without any consideration for data separation. And as the logical capacity becomes full, the reclaim unit handles will allocate reclaim units out of the over-provisioning. So let's explore the relationship between WAF and spare. And for spare, I'm calling this the over-provisioning plus the system area. For a full span random write workload, you can calculate WAF to be about 0.5 over % spare. And for a typical data center standard endurance drive, we'll typically have about 7% OP, maybe 5% system area for a total of 12% spare. And for a full span random write workload, you can calculate the WAF to be about 4.2. Now, as you can see in the other examples in the table, having unmanaged FDP consumes additional OP, which will then drive the WAF higher. So, host software best practices. The host, when enabling FDP, should absolutely employ at least one of the data separation strategies that I mentioned earlier, and not allocate additional reclaim unit handles, as they may inadvertently consume additional OP. And for SSD developer best practices, for reclaim unit handles that haven't received any writes yet, is best not to allocate a reclaim unit. And that's my FDP best practices. Thank you.
Thank you. Hello, my name is David Wang, SSD firmware architect from Silicon Motion. Today my topic is about the challenge in enable FDP in high capacity QLC SSD targeting AI application. Why FDP can help QLC adaptation? So QLC based hyper-density SSD delivered a huge volume to the reader-intensive workload, but very struggle in the writer-intensive and or mixed workload due to the poor endurance and the performance. We think FDP is ideal technology to augmenting QLC endurance and the performance. It can help accelerate QLC adaptation in data center, primary storage, and AI application, enabling low cost per gigabyte SSD. It can dramatically reduce the WAF, improve DWPD, maximize the performance while minimize the negative impact of low PE QLC NAND. We have some tests to measure the performance and the WAF based on the 16 terabyte QLC SSD. The NAND, QLC NAND is a PE cycle is 15K, 1500. So run the FIO random write, the WAF is 5.5. The IOPS is very low, it's 120K. And the DWPD is 0.18. We use the other controlled workload. We can get the WAF is 3. But in the same controlled workload with FDP enable, we get the WAF is 1. And the write performance is 725K. And the DWPD is 0.96. This is amazing. It's almost similar as the TLC SSD DWPD. This page shows some comparison test between the enable FDP and without FDP. So we run the workload is either sequential write with a different I/O size and data temperature. So without FDP, basically all the workload is written to the same super block. So it's similar as one handle. So we can see the WAF is FDP is almost 1, and the non-FDP is 3 point something. So the write throughput, we can see the big difference. Okay, now we talk about the design challenge in the FDP QLC SSD, especially the large capacity is 128 terabyte or 256 terabyte. So first the issue, basically we need to reduce the DRAM use for manage the SSD BOM cost and the PCB area constraint in the typical SSD form factor. The first design, we support the configurable IU size. So basically it's from 4K, 8K, 16K, even 32K is okay. And the second design, we controller use the hardware-assisted bit pack L2P entry to further saving the L2P table size. For example, we use a 33-bit instead of 40-bit can address the 8 gig IU. This can further reduce the L2P size up to 17.5%. So this table we can show with the 16K IU and L2P entry size 34-bit, the L2P size can be 32.9 gigabyte. So this can fit in the U.2 or E3 some form factor. Number 3 is the reduced WAF caused by the small write on the large IU. So now we have the issue is when comes to large IU, but still has a small write. So I think some companies working on how to change the software stack to support the large IU. This is good. But in our side, in the controller side, we're thinking, we just support the mixed IU size in the same SSD. So for the small write, we can let application place the small write to the handle with 4K IU. Next page. The another challenge is to support the multiple namespace or handle the QoS and the performance consistency of application workload could be downgraded due to the unbounded noise neighbor and internal resource contention. So our design proposal is we shape the per namespace read-write performance with hardware engine. We call the performance shaping engine, which is based on dual state token bucket algorithm. So the performance setting can be runtime adjusted and applied through the VU command. So we have some test with the emulated AI workload. It's a mixed read-write on the 4 namespace and the 4 handle in the QLC SSD. In the left side of the diagram, the picture is to show with the less bounded read-write. So the read performance is much higher. This will cause the write performance fluctuate a lot. In the right side, we use the performance shaping to properly limit the read-write bandwidth. We can achieve the good overall performance, and more important is a good I/O consistency. Yeah, you can see the number is the reader consistency is 74% in the without the performance shaping, and with the performance shaping we reach 95%. For the right, it's similar. Okay, just my content. Thank you.
Hello everyone. Today I'd like to talk about how persistently isolated FTP will keep reducing write application SSDs and share our result here. So FTP allows hosts to organize data into different physical location sets, which we call reclaim units or RUs. Hosts can write to different RUs at the same time, isolating data by its lifetime. There are two different types of data isolation here. One is a permanent isolation, another one is initial isolation. So when the SSD controller starts to need to move data during operations like garbage collection, so for the initial isolation, the controller is allowed to move data from different groups and mix them together. But for the permanent isolation, all the data from the different group will stay isolated after data movement. So that is to say, for the initial isolation, different RU's data is mixed after internally data movement, but not for permanent isolation. Here we like to show some typical scenarios in the details. So let's look at the typical scenario 1. That is, let's suppose we have the user data from 2 different groups and we use the 2 different colors to represent them. And we use the shadows to represent invalid data here. So at the beginning, all the 2 groups data are isolated. And after the host writing for a period of time, all data will be mixed up after the garbage collection. So if at this point, all the data from group 1 are invalid, so for the isolation, which is initial isolation, all its data mixed up. So finally, we have to move the group data and to release the right resource. However, for the permanent isolation, all this data will be not mixed up. That is to say, data from the same group will stay together after data movement. So in this example, even for the group data reach its lifetime, and we don't have to move the group 2 data, and can we just release the resource for the group 1 and to reduce the data movement here. Then we can see another very typical scenario. So the previous one, all the group 1 data reached its lifetime at last. But for in this more general case, we think about the regular garbage collection here. That is only part of the group data will be invalid. So all this data at the beginning are same for the previous one example. They are isolated on the NAND. And after rounds of the data movement, all this data will be mixed up in the initial isolation case. And if the part of the RU1 data here are invalid, let's say in order to release the right resources here, we have to move the group and 1, 2 data together and to release that. But however, for the persistent isolation, that is, we can hear for the shadow part, we have the same invalid data here, but they locate at different positions. That is, we can only to move less data to release the right resources. In this way, you could not doing those unnecessary data moving here. So by the examples, you could see there's some red application differences between initial isolation and permanent isolation. To compare with them in details, we will say, like, for the implementation part, the permanent isolation will have high design complexity and use more RAD resources. And for both of the initial isolation and permanent isolation, both of them will have the WA or RAD application around 1 for the sequential lag traffics. However, for the permanent isolation, in the non-sequential lag hosted traffics, we'll have more ideal WA as we show in the previous slides. And also, permanent isolation allow hosts to get aware of how data layout on the physical NAND, they could control the OP of each RU. For in SSD side, the better write application is actually everything will go high, have higher throughput, lower tail latency, and longer lifetime. So we could say here, permanent isolation FDP uses complexity to trade off better WA here. Here we like to show some our test results on our ScaleFlux CSD 5000. In our I/O test, we're using different error pattern and different data value period. We're writing to 8 different RU units group. So this graph shows how the WA will change along the host writing. So we are testing the 3 different cases that for non-FDP, initial isolation FDP, and permanent isolation FDP. So in the graph, we can see that the WA or WAF or read application stays the one, and then it will start to rise up when the internal data movement start, and they will eventually enter a stable state. By comparing the results from the stable state, we could see the permanent isolation outperformers 15% of WA than initial isolation, and 50% of WA than non-FDP. So by these examples and test results, we could say the permanent isolation FDP could keep reducing the WA in real world. Yeah, that's what we want to share here. Thank you.
If I can find the page down button. Okay. Wow, lots to be said about flexible data placement. Quick introduction, I'm Stephen Wells. I'm a fellow solutions architect over at Micron, and I am a boomer. Reason why I say that, I started working on Flash 37 years ago. There were 10 of us at Intel that started this off. And I got to do chip design for about 5 generations, starting with a 256 kilobit flash memory, which we were very proud of as being high density. I had the privilege to present in 1993, 30 years ago, anniversary now, a paper that said the economics at a silicon level of making an SSD out of a large block rather than a write-in-place LBA size block like the rotating guys were doing was economically superior and is going to be the way to go. It also addressed issues around wear leveling and the lack of consistent write patterns that the host applies to the storage device. And those could all be solved with a solution that included garbage collection. And so very, very quickly, for those that don't do this all day long, the host wants to read to a NAND array and the host wants to write to a NAND array. However, because there's this need to relocate data for wear leveling purposes and garbage collection, there's this incremental set of reads and programs that happen to a flash memory device on top of the fact that, of course, you need to erase. So from a latency perspective, and the way you read this is this is a probability chart, latencies of reads while there's this garbage collection thing going on in the background, the reads are impacted because of those relocation garbage collection activities that are going on. And so looking at this, you know, about 1 read in 100 collides into a program that's going on, and about a 1 read in 10,000 runs into an erase. And that's predominantly a function of you do many erases before you do a single, or many programs before you do a single erase. So in the process of trying to mitigate the impact of this garbage collection and to understand what it is and try to do this, we've had many, many attempts. Javier, I think you have the official count, but it's on the order of 5 attempts in standards bodies to try to come up with this. And we feel that flexible data placement, we finally have landed on what we believe is the winner in this, or one of the bests we've seen so far. I did have to follow Meta and their use of AI in their pictures here. So this is the 800-pound gorilla in the data center is the gorilla doing garbage collection. And it's all of its impacts that everybody's talking about. It impacts the endurance of the flash. It impacts the power of the flash. It impacts the performance of the SSD. And there's one other that I'm going to talk to about today, and this is also that I showed from that diagram. This also impacts the latency outliers. Why do we care about latency outliers? Well, there's a great paper published by Meta a few years back that discusses that in reality, you pick up your phone, you open up Facebook. It's literally, it generates a critical path of thousands of subqueries in fork join scenarios, each of these chained very, very deeply. And so what happens is if you have a latency outlier at even one of these points here, all of those other queries that happened can't realize the benefit of that. And this is why, especially in a hyperscale environment, latency outliers are critical to manage. And as we've said, the garbage collector, with all of its 800-pound gorilla-ness, is impacting the latencies. And I realized for all of the data we've seen on FDP, I've not seen direct data discussing the latency of outliers. So this is an experiment that we ran here. This is comparing the latency outliers of running a random read workload in a firestorm of random writes as well. And those random writes are not only are inducing the garbage collection. And without an FDP configuration with a write amp of this particular drive's data, it was about a write amp of 3.3. And so, median latencies were this number for a read, and then you could look out at, 1 in a million read latencies were sitting out in here. Now, with the garbage collector quieted down, and I took it all the way to the extreme, with the garbage collector completely quieted, a write amp of 1, you can see that there's an improvement in these latencies. It's not just the tail latencies that are improved by 30%. You're getting tail latency improvements even all the way up into the medians in this. And given how critical latencies are, especially in a hyperscale environment, in a scale-up environment, the fact that these latencies can be quieted is a big deal. And so it's on top of everything else, saving on power, saving in endurance, and saving in incremental performance. The latency outliers is an important one as well. And this is, at least for me, the first time I've seen any of this. Follow on if anybody's interested. This came from a blog post that I had done that digs into this a bit deeper on why latency outliers in data centers matter and how Micron, we believe, became best in class. Thank you.
We now have time for Q&A. There's a mic over here and a mic over there. So feel free to come up to the mic and ask our panelists questions. This is the opportunity.
Just a point of clarification and to help support the FDP movement here, SandBlaze offers a full test suite that includes write amp capabilities to allow you to go ahead and further develop your FDP technology, and I'm happy to discuss this offline with anybody that's interested.
Great, thank you. Looks like we have another question over here.
Yeah, so Jaja and John Michael, you guys both showed data, for FTP, different workloads, obviously, because the data has told different stories. Can you guys explain the workloads that each of you had? The benefits of persistent versus isolated. JM, you were focused on the non-persistent, and Jaja was focused on the persistent. So just to understand the workloads would be good.
Okay, you can go.
Yeah, if you go back on the OCP YouTube, maybe like a month ago, I came into the OCP storage project and presented a couple of the other experiments. I ran RocksDB in these multiple namespaces, and with one of the FIO synth scripts that simulates RocksDB, and that one does random writes. And in that scenario, where it was initially isolated with these, the RUH per namespace did not help WAF, but it did help latency, which was very curious. So in these workloads where there's going to be some random writes mixed in and the velocity of writes is going to be high, that's where you're going to want persistent isolation. But the initial isolation is good for these workloads that have sequential writes and of different block sizes.
Yeah, so for our part, like say, for internally we did do the test on the both like the sequential like traffics and randomized data traffics. Here what we show here is more about randomized randomized data pattern here to show the differences between the initial isolation and the persistent isolation here. I think for the sequential data pattern in our test, as long as the host can leave reasonable over-provision out there, I think both of them, the replication can reach the one, which in the ideal way. Yeah.
Great, thank you. Next question over here.
CJ Newbern from Intel. Whoa, man. That's still in the genes 8 years ago. I'm at NVIDIA. Still trying to flush that out of the system. But every couple of years I slip up like that. I've talked to you a number of you already about the possibilities and challenges with reducing tail latency as we get just a crazy number of accesses coming out of the GPU. This is kudos, really great to be able to see multi-x improvements in performance and power effectiveness here. What do you think are some of the remaining things that are on the table to continue to improve and extend FDP with the goal of being able to reduce that sort of max tail latency that we're seeing in some of these cases?
Steve, you want?
Good question, by the way. Your mileage will vary is maybe the best answer to give on this, as several of the other presenters had presented. If the data is placed well, the garbage collector is quieted, that is the biggest inducer of the tail latencies that you run into. So it's going to be a matter of, for the kind of workloads that you're dealing with, is experimenting with the various options to how to place the data initially, and then deciding whether you want persistent isolation or initial isolation as a configuration. Because as Jonathan pointed out, there is impacts to the persistent versus initial isolation. And I think exploring possibilities of finding the right number of handles, the right RU counts and sizes that make sense in here. This is some exploratory. It feels early days still on this, but it feels like there's going to be optimizations that happen. And I think the most important thing that we get from flexible data placement is yeah, there were other options that would guarantee you a right amp of 1, but if you didn't have a perfect implementation, it would throw an error and you were done. And so this one allows you to just improve it until you're happy, and then that's good enough. So, or you run out of money and you need to move on. Did that answer your question, CJ? Or
It's progress. While he's passing the mic, we're very interested in setting up a framework for the community to be able to do such explorations with workloads, real hardware, and looking at sort of defining the next generation of hardware that can do that. So happy to talk to more people about that.
Yeah, and I'm just going to follow on with a comment that NVIDIA's use case is typical of largely highly parallelized distributed systems. Steve pointed out a meta paper. There's also a wonderful Google paper called The Tail at Scale, talking about these tail latency issues. And I would say there's active work going on by the drive vendors. I know particularly I'm very heavily engaged in addressing the long tail latency in our devices, because we realize that it does have an effect on these distributed systems and is critical to your performance. So there are some things that we're talking about internally and experimenting with, but we don't have hard results yet, but it's definitely a pain area that we're aware of.
Great, thank you. More questions? Okay, then we can go to our next talk on SPDM, but let me first thank all our speakers here and all the time they put into this, so thank you very much.